two big ideas for our next section of the course are energy and work. And so let's start by thinking about how we often define these two terms. So energy is often defined as the ability to do work. But of course work is defined as a transfer of energy, which means we kind of have things sort of working in a circle here. So how are we going to deal with these two ideas? Well, what we're going to choose to do is say something in here is so fundamental it's hard to define. And that may seem a little bit weird, but if I asked you to give me a really good definition of time, you'd probably struggle with that because time is a very fundamental concept. It's hard to define in terms of other more basic words. We're going to say that energy is that same kind of idea. It's such a fundamental thing, it's hard to actually talk about in terms of simpler words that you can use to define energy. So then what do? If we don't have a good definition for it, well, the most basic thing we do is we learn how to recognize forms of energy. We in this class are going to focus on kinetic energy and several different types of potential energy. But in other classes, you might talk about chemical energy or electromagnetic energy or nuclear energy. Step number one is sort of recognizing when energy is present. Step two is figuring out how to keep track of it. We will use the work energy theorem as our starting point for keeping track of energy. We'll eventually end up building that into a framework that will lead to the idea of conservation of energy, but we're going to start with the work energy theorem as our basic bookkeeping method for keeping track of energy. And the third idea here, and again this one probably is of more practical importance, is recognizing that work and energy are scalars. And mostly what that means is, unlike the vector problems that we've been working in the class up until now, our scalar problems are going to be we're going to be able to sort of wash out a lot of these details that make the math complicated. So using work and energy as a general rule is simply an easier way to get the answer that you want. We don't have a very good definition for energy, but having decided that energy is the fundamental concept here, this means that we can now have a very clear definition for work in terms of energy. So work is going to be a transfer of energy, and in particular a transfer of energy that's due to a force acting on an object as it moves. So if you have a force that acts on an object while that object is being displaced, that force does work. If that force is constant, then we can calculate the work done by a constant force on an object as the object moves through a displacement by the equation below. So the work here is the dot product of the force, the constant force, with the object's displacement. And so again, because in this class we're going to mostly work with problems that are two-dimensional in nature, it's probably easiest for us to frame this in terms of the geometric way of thinking about a dot product. And so we're going to talk about the work done by a constant force is going to be equal to the magnitude of the force times the magnitude of the displacement times the cosine of this angle phi, which is defined to be the angle between the force vector and the displacement vector. So as an example, let's say I've got a box. There's a constant force that acts on the box as the box moves across the surface to the right. In calculating the work done by that force, I'm going to draw out those two vectors, the force vector and the displacement vector. I'm going to draw them from the same origin because that makes it very easy for me to see the angle phi, which I need to plug into that cosine function. So once I've sort of made this drawing, then calculating the work is relatively straightforward. It just says what's the magnitude of the force, what's the magnitude of that displacement, and what's the cosine of the angle between those two vectors. So let's think a little bit more about things that this equation is trying to tell us. So for starters, let's think about units. Well, the units of work are basically going to be the units of force plus the units of displacement plus the units of cosine theta. So let's deal with the cosine theta piece first. Again, theta, the angle itself, has a unit, right? Whether it's radians or degrees, there's a unit for theta. But cosine theta is just a number. cosine theta itself is unitless. It doesn't contribute anything. So the units of work are going to be units of force, which are newtons, times the units of displacement, which are meters. So one way to talk about the units of work is that it is a Newton meter. This comes up so much, we're going to give it its own name. We're going to call these joules. And in SI units, a joule is a kilogram meter squared per second squared. So a Newton, we said, was kilogram meters per second squared. Now we're multiplying Newton times meter, so we get kilogram meter squared per second squared. One of the things we'll go ahead and emphasize now is that the joule is a unit both for work and energy. Again, because work is merely a transfer of energy, that means that work and energy have to have the same unit. The second thing this equation is telling me is that you get the maximum work when the force and displacement vectors lie along the same line. And basically that's because you're not changing the first two terms. The magnitude of the force is still the magnitude of the force. The magnitude of the displacement is still the magnitude of the displacement. What you are changing is the relative direction between those vectors. And so you get the maximum work when both the force and the displacement lie along the same line and either point in the same direction, so that the angle between them is 0 and therefore cosine phi is positive 1, or they point in opposite directions. In that case, the angle between them is 180 and the cosine of phi is negative 1. Either way, you get plus or minus magnitude of the force times magnitude of the displacement, and that's the largest value you're going to get for the work. Now, of course, the smallest value you're going to get is when no work is done. And that's going to happen when the angle between those two vectors is 90 degrees. So if the force acts perpendicularly to the displacement, then the work done by that force is 0. Work can be positive, it can be negative, it can be 0, and that depends on the angle between your two vectors. If the force has a component that points in the same direction as the displacement, that means that the angle between the force and the displacement vectors is somewhere between 0 and up to but not including 90 degrees, then that force does positive work. What that means is that force is acting to help cause the displacement. On the other hand, if the force has a component that points in the opposite direction as the displacement, which means that the angle between them is something just past 90 degrees all the way out to 180, then that force will do negative work. A force doing negative work means that that force is acting to hinder the displacement. Third option, 0 work. That comes when the force and displacement vector are perpendicular to each other. So work is a scalar. It's a scalar that can be positive, negative, or 0. So let's think about this equation a little bit more. And here we'll just rewrite it so that instead of the magnitude of F, we'll just write F. Instead of the magnitude of the displacement, we'll just write that as d. So you can think of this as the same equation. We just sort of simplified the notation a little bit. But what we want to do here is we want to think about how we can pair that cosine term with either the force or the displacement. And so for starters, let's think about if we've got the displacement along the x-axis here. I can pair the force and the cosine. Since phi is the angle between the force and displacement vectors, then F cosine phi is just the component of the force that points in the same direction as the displacement. So we can rewrite that as F parallel, because what it's telling you is that only the component of the force parallel to the displacement is going to do any work. The component of the force that's perpendicular to the displacement, that won't do work because of course it's perpendicular to the displacement. So that's one way that I can rearrange my equation. The other way, and this tends to be useful if my force is the one that lines up with a coordinate axis. So here, say I've got a force that points straight down. I've got a displacement that points off at some angle. But if I think about now that d cosine phi, well again, phi is the angle between my two vectors. So that delta r parallel tells me the component of the displacement parallel to the force, and that's the only component of the displacement that's going to do any work. What if we have multiple forces acting on our object as it moves? So here, again, let's look at an example where we'll focus on 3 forces that act on this box. So force 1, force 2, force 3. And we'll let the box move, and again, it'll slide to the right. So I've got a displacement vector that points to the right. So for starters, we want to make sure that we focus on the work on what object by which force. So when we talk about the work, really what we mean is the work on what by what. And so we can go through and think about all three of these forces do work on the box. We'll assume these forces are constant, and then I can calculate out what the work is that's being done by each individual force on the box. So for force 1, again, I'll use my equation. And for force 1, I know that I want the displacement vector at first force, force 1, and then I've got an angle here that I'm going to label phi 1, that is the angle between those two vectors. And again, because this is an angle less than 90 degrees, I know that the work done by force 1 is going to be positive. Force 2, it is perpendicular to the displacement. So what I've labeled as phi 2 here, which is the angle between the displacement vector and force 2, that's 90 degrees, which means force 2 does no work as my box slides to the right. And then force 3, it points back in the opposite direction. So here, what we've labeled phi 3 is 180 degrees, which means that force 3 is doing as much negative work as it can, right? So it's clearly going to be negative. And again, because you've turned that cosine into a -1, that means the work done by force 3 is as large a negative value as you can get. Calculating the work done by individual forces is going to be critically important in terms of putting together the work energy theorem. So this is something that we're going to want to become very comfortable with. Well, what if the force acting on our object isn't constant? So everything we've talked about up until now is for forces that are constant as my object moves through some displacement. So if we consider a force and a displacement that lie along the x-axis, so let's start by thinking about a one-dimensional thing. So we have the x component of the force plotted on the x-axis, we've got the displacement in x plotted on y, and if we're interested in figuring out, well, what's the work done by the force as the object moved from this position to some final position, well, what we can do is say, well, that's not constant, but I can basically think of this as little pieces where I can treat it as if it were constant. And so here I've got some little delta x. It's not too wide. And again, it's not exactly constant over that, but it's reasonably close. It's certainly more constant than what it was over the entire from xi to xf. And so I can sort of fill that in. And what that does is it lets me break up this gap where the force isn't acting constant into a bunch of little segments where I'm now starting to treat it as if it is acting in a constant way. And so what I can do then is just basically add up, well, what are all, and so how much work did it do over this stretch where I'm acting as if it was a constant force at this amount, plus how much work did it do here where the force was this amount, plus the work done where the force was this amount. Do that over all my segments, and that's going to tell me what the work was. If I start with a lot of discrete segments like this, that's going to be an approximation. But of course, as I make my segments smaller and smaller, so in the limit that these sections become thinner and thinner and thinner, then in fact I get closer and closer to where the work I'm calculating over each section represents the work that was actually done over that tiny interval. And of course I realize that if I'm taking the limit as delta x approaches 0 of this summation, really what that is I've got an integral. So in general, for a one-dimensional example, the work is the integral from some initial position to some final position of f times dx. If I want to think about in multiple dimensions, then I just put that dot product back in. The most general way that I can talk about work is it's the integral from some initial position in 3 space to some final position in 3 space of the dot product of some changing force vector with infinitesimal little displacements. And of course, if we think about what this general definition gives us, well, again, it brings us back to where we started. So we still have this dot product, which means fundamentally this is creating a scalar. It's taking two vectors and building them into a scalar, and then I'm just adding up, that's what my integral tells me to do, a whole bunch of scalar values. That's going to give me work. Because that dot product cares about how these two vectors line up, What it means is the contribution to the work over each tiny little step will be positive if F and dr project in the same direction. So here I've got a force that points up and to the right, my displacement's to the right, which means that the projection of that force points in the same direction as the displacement, and so the work over this little infinitesimal step dr will be positive. On the other hand, if my force points back this way, then its projection points in the opposite direction as dr, and so the work done by this value of the force over a tiny little step would be negative. And of course, if that force is perpendicular to that tiny little displacement step, then it does no work over that infinitesimal piece. So the same rules apply whether the work being done by a force is positive, negative, or zero. It's just that now I have to think about that over all these infinitesimal little steps dr and add that up to get the total work done by the force.